Hello everyone, welcome back to the channel. I'm Arjun Narula and I'm back with another Verilog project which is N-bit multiplier with binary to BCD converter. So before getting started, first of all, I like to point out one thing, which is that 99% of you have still not subscribed to the channel. So if you're new to the channel, please consider subscribing. It motivates us to bring out more such content. So now let's get started. So what we'll do is that we'll create an n-bit multiplier of two numbers. It will multiply using shift and add algorithm. And finally, the answer, which would be in binary form, would be converted to a BCD using double dabble method. In the end, the output will be displayed in both binary and BCD form. So let us see how can we convert a binary number to a BCD form. We have a number 151, which in binary is represented as this. Now, if this number we had to convert in BCD, in theory, it was a pretty easy task, right? We would have assigned just 3 nibbles and the lower nibble would have gotten the number 1. The middle nibble would have gotten the number 5 and the highest nibble would have gotten the number 1. So this was this easy. But in reality, in computers, this does not happen. So what happens? Let us see. So for the double dabble algorithm, I'll just give you a one statement which will solve entire thing for you, which is if the number is greater than 4, you add 3 and shift, otherwise you shift, right? So now the number is 0. So you simply shift. Here we have shifted. Again, the number is 1. You simply shift. Again, we simply shift. Now the number has become 9. So what we do is we add 3. We add, what do we add? 3, 0, 1, 1. Now, once we have added, we again shift. Again, we add 3. Now, we again shift. Again, we add 3. Now, we again shift. So this way, when we reach to the answer is this only, what we had written in theory, right? So now, let us look at the flowchart of the problem. So first of all, how we'll go is that we'll start. We'll say that if reset is 1, then we'll reset the clock and the input. Now, if reset is 0, then we'll start and we'll see if start is 0, we have a variable start. If it's 0, then we store the values of A and B, set the bits and initialize the output with 0. If start is 1, then we'll check B0, which is the 0th bit. If it is 0, then we'll simply shift, right? So in the simple multiplication, which we saw earlier, if it was 0, we simply added a placeholder, right? So we'll simply shift. If it is 1, then we'll add the multiplier again. So that will be the same thing, right? We'll add the multiplier, right? And then shift, right? Next, we'll reduce, left shift by 1. We'll reduce the bits by 1. And finally, we'll convert the output to the BCD, right? So now let us get started with the Verilog code. Here we have parameterized n as 8. Now what I need you to understand is that we have made a generalized n-bit multiplier, and here n could be anything, 8, 16, 32, 64, 128. But for the sake of understanding, I have here taken n as 8, right? So now the output of the multiplication of two 8-bit numbers could maximum be 16 bits, right? So here the output is of 16 bits if we put n here, right? Now for the BCD output, this part is a bit tricky. What we have done is we have divided that output into parts of 3, then added 1, multiplied 4, and eventually subtracted 1, right? That this one subtraction is because it is from 0 to that number, right? So if we have 16 bits, it is 0 to 15, right? So now what we do is we declare the inputs, we create the reference registers. Here we are doing nothing, just creating the registers, right? Standard theory. Next, we have the continuous assignments. Next, we have, now if you remember the flow chart, now we have the reset. Now, if the reset is 1, we reset the clock. If the reset is 0, then we start, right? So now we have the case statement with start. Now, if start is 0, what we'll do is we store the values in A and B. We'll set the bits and we initialize all the outputs as 0, right? So now, if start is 1, right, what we do is shift and add multiplication. So what we are doing is that A in register is getting shifted to right so that the next bit could be multiplied, and B is getting shifted to the left for the place of the placeholders, right? here bits is a variable which is getting decreased by 1. Now if bit gets to 0, then the multiplication is completed, right? And now here, what we are doing is that we are checking the values by hard code, that if whether we need to add 3 or not, right? So if the particular number is between this range, then we'll have to add 3 or not, right? So this is what we are doing is when we use the double dabble algorithm, right? Next, we have the test bench. What we are doing is here we have declared the inputs and outputs, simply initializing the multiplier. Here we have created clock using forever loop. Next, we have the test inputs. So now we have two test inputs. First one is we'll multiply 26 and 30 in decimal, which is written in decimal. Then we'll multiply 13 and 13. Now let us see the results. So this is the simulation which we'll be looking at. So first of all, we multiply 26 with 13, right? So as soon as the finish signal gets high, here finish signal gets high. So we get the answer as 780, right? Now to see the 780 in BCD, what we do is, so first four numbers, right? So this is actually a 16-bit BCD, right? So first four number here, I just cross out them. Next four will represent 7. Next four represent 8. And the last four represent 0. Hence, the answer we have got is 780, right? In the similar way, 13 to 13 multiplication is also correct, right? Next, we have some of the observations. The out represents the value of the multiplication, value 1, when finished signal gets to the 1, right? Here we discussed it. As soon as the finished signal gets to the 1, our multiplication is completed, right? Then we have this simple things which we have already discussed. This marks the end of the video. If you have reached till here, please do consider to like the video, share the video, and subscribe the channel. Here, I would also like to thank Mehak Goel, who has put an immense effort in this project and has written the code in Verilog. You can find the Verilog code in the description, and do write your queries in the comment section. Also, if you are wondering which book should you buy to study Verilog, I have written 2 books in the description. If you want to buy, please do consider buying from the link. It really helps the channel. Thank you.